Okay, cool. Hello, everyone. I'm Shunyang Wang from Oliver Finn and Dean Cantillo Lab. Today, I want to talk about quantum chemistry and electron ionization mass spectral prediction. In compound identification, reference spectral library is used to match experimental spectra and get structural information. But this approach is limited by the amount of available reference spectra. For example, there are 102 million compounds in the PubChem recordings, while only 40 million of them are commercially available. The EMS database NIS17 only has 0.27 million compounds. Typically, only 20% of metabolites can be identified in the untargeted MS screens. To close this gap, generating in silico mass spectra can help us get spectrum from the structure. There are many classic methods, such as Mass Frontier, Lipid Blast, and CFMID. All those methods are limited to empirical rules, while QC-XMS is a quantum chemical tool from the first principles, and it can predict EI and CIDMS. Today, I want to discuss the EMS prediction. We tested QC-XMS on hundreds of molecules, got an average dot plus score of 635. A dot plus score of 1,000 means perfect match, and a score over 650 considered as a good enough simulation. We can notice that the similarity score of nitrogen-containing compounds like amides and amines are better than the oxygen-containing compounds. The simulation of aromatic compounds is more accurate than the aliphatic compounds. The average processing time is 1.5 hours with 26 atoms per molecule on a 44-thread CPU. The processing time and the molecular size plot shows an algorithm complexity of order n squared. These results indicate that QC-XMS is a well-parallelized program. Here, I showed a pair of in silico and reference spectra of urocanic acid with dot plus score of 897. The high quality in silico spectra shows most of the ions correctly, except these 4 green peaks. All those 4 peaks are caused by rearrangement reaction and have 1 hydrogen shift away from other strong signals. This observation is quite common in our simulations. If we can predict these reactions correctly, we can get about 15% increase of similarity score. Now the problem is that a comprehensive molecular dynamic simulation of rearrangement reaction could be extremely expensive. Luckily, we do have a potential solution. Here, I showed the moving average trend line of the electronic energy change in 2 trajectories from the simulation. The blue line is a simple bond dissociation reaction, while the orange line is a rearrangement reaction. We can observe a drastic energy decrease in the hydrogen shift reaction because of the forming of new bonds. With this energy change pattern, we can easily detect the rearrangement reactions and adjust the intensity of this reaction empirically or using machine learning. In conclusion, QC-XMS method is suitable for generating large-scale in silico database, especially for aromatic compounds and nitrogen-containing compounds. While the rearrangement reactions are important to improve the method, and in the future, if we want to build a library of 100,000 molecules, it will take us 3 months or 5,000 calls. With that, I want to thank all the group members, and I'm willing to take questions from the chat.
Yes, questions into the chat. Thank you. Excellent. Thank you,